Okay, hello folks. You probably guess what? I've lost my pen. Can't blame you lot now, can I? Anyway, hello. This is Matrix lesson 7, and it's the last of the new stuff really, because the next lesson's just a bit of a summary. So I'm fidgeting for that something pen. Just let me press a pause. So today we're going to learn about what is meant by diagonal matrices and be able to use diagonalisability for 2 by 2 and 3 by 3 matrices, and we've got to apply method of diagonalization for the reason to evaluate powers of matrices, which is what it's all about really. So it's bringing in the eigenvalues and eigenvectors again. So let's move. For diagonal matrices, a matrix is said to be diagonal if the following two conditions are met. 1, its non-zero entries only appear in the lead diagonal. 2, all other entries are 0. So these are examples, these 3 here. All they've got numbers on the lead diagonal, which is in red, and all the other values are 0. It doesn't matter if a number in the lead diagonal is 0, as long as all the others are 0. So all those 3 are good examples. Right, decomposing a matrix. You are used to factorising a number or an algebraic expression. So it said 12 is 2 times 2 times 3. Or factorising x to the 3 minus x would come out as x bracket x minus 1, x plus 1. There must have been a difference of 2 squares in that when you pull the x out. Anyway, we can similarly, I can't say that word, similarly decompose a matrix into a product of matrices. There are a few varieties, established techniques of decomposing a matrix. Here's one for just for random interest. You could get the LU upper lower or lower upper, getting them right way, decomposition. We can rate a matrix as that and that. Interesting. Matrix decomposition into lower triangular and upper triangular matrix, or more on what we're doing, we're going to be doing the eigen decomposition. Woo! Where M is UD, U to the minus 1, where U is the column of the eigenvectors of M, and D is the diagonal matrix where the diagonal elements are the eigenvalues of M. And U to the minus 1 will just be the eigenvectors inversed. All right, this is a decomposition method we will be covering today. But why? Well, decomposing a matrix can help us the efficiency of finding powers of matrices and a whole lot of other stuff should you wish to go to university to do more, which I'm sure you all will. Right, once you've known all this. So when the transformation matrix M is applied to V, remember V is the eigenvectors, the result is a scalar multiple of V. This gives us the equation that we've been seeing for the last few weeks, MV equals lambda V. Remember, lambda's the eigenvalues and V is the eigenvectors. So for each eigenvector, the lambda is the corresponding eigenvalue. If M, say, is a 2 by 2 matrix, it can have 2 independent eigenvectors and eigenvalues, and we can say that MV1 equals lambda V1, and also a different equation, MV2 gives us lambda 2 V2. If we wish to create an eigenvector matrix, we could write this. See, put the vectors in columns here, so that'd be a 2 by 2. Could be written as, using this, the right hand side, lambda 1 V1, lambda 2 V2, 2. And taking that, because these are just scalars, you can take them out and write it as the vector v1, v2 with lambda 1 on there and lambda 2 on there. And hopefully if you see, if you multiplied that out, you just get back to that line there. Right. So calling the matrix of eigenvalues U and the lead diagonal matrix of the eigenvalues D, we now have UMU, so that's your V1, V2, equals your V1, V2 times that lambda naught, naught, lambda, naught, lambda, oh gosh, that one, lambda 1, naught, naught, lambda 2 as your D. So now, as long as U is non-singular, that means it'll have an inverse. And when it has an inverse, it'll have to be that there were two non-parallel eigenvectors of M. Basically, you can't have, it would fail if you'd had two repeated eigenvalues or roots of the characteristic equation, and you could not find independent eigenvectors. So basically, if your lambda 1 was, let's say 2, and your lambda 2 was in fact 2, and you found your eigenvector as 1, 1, and the other one as 2, 2, they're not independent, so this method wouldn't work then. But if they are singular, there will be an inverse. You can inverse on that side. So we've got to, if we're inversing on the right, we'll have to inverse on the right of the other side. We get that thing. Now we know that U and U inverse, opposites or whatever, they make I. So you just get MI, and you might as well just write that as M, equals U d U to the minus 1. Fantastic. And you can more generalize that by saying if it's an n by n matrix, then you'd have n lots of eigenvectors with associated n lots of eigenvalues. Then you could write M as a diagonalized form of this thing, where U is the eigenvectors and D is a diagonal matrix with your eigenvalues on the lead diagonal. Woo! Secret is 500 by 100, but thankfully we won't. Right, the matrix has eigenvalues associated with eigenvectors. Thank God they've been found for us. Write M in the U du to minus 1 form. So we scribble that out because I've said write M and I've given it A. Let's put M then, don't confuse me. So M will equal U. Now U is the eigenvectors. D is the eigenvalues on the diagonal. And U inverse, I'll use my machine. So you put your matrix in. So to do that, you need to go into run mode. Press F3, change one of those to a 2 by 2. Put in 1, 1, 1, minus 1. Then you need to come out and press Option F2, F1, matrix alpha D or whatever, alpha, whatever you put it. I'll put it minus D. Then to power minus 1. And you should, ooh, I don't know if I can get that in. So you put him in, ooh. Very good, D to the minus 1. Anyway, you get a half. Hopefully you can do that. And then you need to put them in as mat. So you put them in as mat. Whatever you call that, so we called it A. And then times mat B, so you have to put them in as another matrix, and then mat A hat. That's one. So if you put those three in and multiply them together, you will get, here's one I did earlier. If you had Blue Peter when you were young, I don't know if that was abolished. But you could do these by hand if you were thrilled by this. Oh, luckily I've not done the answer. Oh. Oops, it's all right, I'm going to have to do this. How interesting can this be? Right, so exit to, here we are, 2 by 2. So putting in that eigenvalue thing, you'll put 1 in and a 3 in. Exit. So do what I said. We put in mat, whatever you called it. You can actually get mat by pressing Shift and 2 if you prefer. So alpha, whatever letter you give it, times mat, whatever letter you gave it, times mat. Put this one as in as your letter to the power minus 1. And out comes the answer, which is looking at 2 minus 1 minus 1, 2. Let's hope you got that too. Right on my notes, now I don't have to do that ever again. Right, super. Now, okay. Your turn. See if you can do the same thing. Oh, just before I go, that was really silly because I should have known it was going to be that. Because that's M. Look. Woo! Woo! We got it right. That's just a decomposition form of that. So it's obviously going to be the same, isn't it? Right, your turn. See if you can prove. Let me scribble that again. That's to confuse you. That's no. But the decomposition form is the same as that. Have a go. Press pause. And here comes the answer. There's a decomposition bit, and you can multiply that out as your calculator, and you would find it give you that. I'm sure you did it. There we go. Right, next bit. So using the diagonalized form to find powers of matrices. Why is it good to write it as that? Well, let's see. So if your m's in that form, m to the power 1003, or just k, you would have basically this thing, u du to the minus 1 times u du to the minus 1 times u du to the minus 1. Oops. Times, I'm running out of space, so I'll put dot, 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 dots, u du to the minus 1. You should only have 3 dots, but never mind. That's done k times. I don't like that. Let's rub that off. Right. So there we go. Now, you might, if you're observant, realise when you've got two of them together, an inverse and a thing, they're going to kill each other. Die. Dead. That one goes with that one. Right, so we're left with basically a U there, lots of D's, and if there are K, lots of these brackets, that'll be D to the K. And then on the end, there'll just be that, U inverse. So, wow. Yeah. It's going to be easy. So because D is a diagonal matrix, we can write D to the power K without needing a matrix multiplication. You just put your lead diagonals to the power K. Very easy. Let's see. Just in general, if you've got M to the N, then that's U to the D, U D to the N, U to the minus 1. Which is convenient because powers of a diagonal matrix can be easily calculated. All right. Oh well, move on quick before anybody says anything. Right. Here's a question. So we're given M has eigenvalues and eigenvectors. Express them in the form u du to the minus 1. So u the eigenvectors. D is the eigenvalues. Oops, you're putting a 2 there, you twit. And the inverse of that thing, there, do it on your calculator. So I have to put back into blooming matrices. Yeah. So, sorry about that, right, so it's a 3 by 3. We put in there 1, 1, 1, 1, minus 1, minus 1, 1, 1, 0. Oh, it's not a 1 in there, it's a minus 1. So easy to make an error. Right, and then you can do inverse of that. So exit and then do your power minus 1. And what you get is this. There we go. And so that's in our form, u to u to the minus 1. But it's not all over there because they want m to the n. That's n. So m to the n will be our u, that's that thing, our d to the power n, and our u inverse, where n is odd. Right, off we go then. Let's write those out. So a bit more space. You might have to write small. What were they? 1, 1, minus 1. 1 minus 1, 1. 1 minus 1, 0. The eigenvalues that we're going to now put in as 1 to the power n, 0, 0, 0, minus 1 to the power n, 0, and 0, 0, 2 to the n. And your inverse matrix right. So you can change that if you like, write them again just because it's happy days. Try not to make a mistake though, but these, anything to power 1 to the power anything is 1. Now minus 1 is power of n is odd. So any minus 1 to the power any odd number is minus 1. Try that yourself. Minus 1 to the power 3, minus 1 to the power 5, so it would be minus 1. 2 to the n, we don't know what that is. Right, can't put this in your machine, unfortunately, when you multiply them out because you've got 2 to the power n, so you've got to go for this by hand. It's a bit of a rascal. So down there you get 1. It's 1, 2 to the n. Down these you'll get 1, 1, minus 2 to the n. Down these you get minus 1, sorry, I'm losing my plot. Oh, minus 1 and 0. Not too bad, but when you get these halves in, it gets a messy thing. Get this right. So that cancels each other out, so you get 0. Get minus 2 to the n. That time you get minus 1 minus 2 to the n. And coming down the middle, we get 1. We get 1 plus 2 to the n. And we get 1 plus 2 to the n. On the bottom we get minus 1 minus 1 and exciting minus 1. Right, let's enter. Done. How can you prove it to yourself? Well, you can. If you do m to the 3, now if you put this in your calculator, you have to put m in. M is, what's m? Lummy matrix, yes. 0, 2, minus 3. That's minus 2. 1, 3, 3, minus 1, minus 1, minus 1. So somewhere, if you put that in your calculator, however you like to do it. So I put that in. Could obviously pick a bigger number than 3. So now exit option matrix mats. Put a powerhouse one. And you get from your calculator 0 minus an half minus 3 halves 1 3 over 2. What do you? Wait a minute, already. I've done that wrong. Oh, I've done that wrong. Ignore me. Sorry. Delete. 3. You get. Oh, you're an idiot. You get 0 minus 8. I'll get my rubber out. Goodness for the rubber. Right. So you get 0 minus 8 minus 9. 199 minus 1 minus 1 minus 1. And if you put 3 into here, let's see if you get that. Minus 8. That'd be minus 9. That'd be a 9. That's a 9. And the minus 1's are on the bottom. Fantastic. Super, it works. Our decomposition form works. So you could work out m to the 703 and put it in there and impress your friends. But you can't have friends at the moment, can you really? So never mind. 2 meter distance, they might be interested. Right, moving on. Example 3. Oh, they're not giving us the eigenvalues and the eigenvectors this time. We've got to work them out. Is that good or is that bad? I'm not sure. How long have we got? Right, so looking at it, there's our there's our matrix M. Let's get these eigenvalues and eigenvectors. To get them, we have to solve the characteristic equation, which was that thing. I won't go into the deriving that again. There it is. So we need to find what the derivative of that thing is when it's, and we need to be equal to 0 because it's not allowed to have an inverse, if you remember. Anyway, so here we go. So I've taken lambda off the diagonals because I've just put that minus lambda I in. So you have to expand this little beast. So you've got 1 minus lambda using the top row with the matrix 6 take lambda minus 1 minus 2 and a 4 take lambda. Then you'd have plus, no, you wouldn't even minus 4 lots of the matrix minus 1 2 minus 1 4 take lambda, and then you have plus, oh, it's plus minus 1 of the matrix minus 1 2 6 take lambda and minus 2. Wow, this is going to be fun. So multiplying that out, you're going to get 1 minus lambda, oh good grief, 6 take lambda, 4 take lambda, and then take the diagonal, so take 2 minus 4, and I have lambda take 4, take away, so it becomes plus 2, and the last one we have minus 1, so I won't bother writing that. 2 take 2 lots of 6 take lambda. Right, working that out, we've got 1 minus lambda, expand those brackets, We're going to have 20, 42, 22. We're going to have plus lambda squared, and we're going to have minus 10 lambdas. Then we're going to have minus 4 lambdas, and then make minus 2, don't they? That right around, yeah. Minus 2. So minus 2 times minus 4 plus 8, is that right? And then we've got minus 2, got minus 12. No, we've got plus 12, and that's minus plus 12, and minus, so be 2 lambda, then that's a minus 2 lambda. Now if we put, oh god, we're going to multiply again. Oh, good grief. So we have 22 plus lambda squared minus 10 lambda, and times 3 by lambda, you've got minus 22 lambda minus lambda 3, and then plus 10 lambdas, and then here if we put these together we've got minus 6 lambdas, and I've got 6 plus 12 is 18 plus 18. Put all those together, we've got lambda to the 3 and minus 1. We've got, all this equals 0 by the way, doesn't it? Yeah. How many lambda squares? Just 1. Done that right? No, those are lambdas. Oh. Yep, it was just 1 lambda squared. Oh, it isn't. I missed them off. I haven't done that. Where did that? 1, then lambda squared, and that times that, times that. That's why I made the square off, isn't it? No. So we've got 11 lambda squareds, and then we've got minus 38 lambdas apparently. Yeah, so 22. Yeah. So 32. Actually 38, isn't it? So minus 38 lambdas, and then plus 40. Right, solve that on your machine. I'm not going to do that. That's an 11, by the way. Come on, 11. Ah, disaster. Let's drop it to 11. Clear. Plus 11 lambda squared. Right, solve that on the machine because I'm not doing that. Polynomial, and you'll get lambda equals 5, 4, and 2. Super. So there are our eigenvalues. What we're going to do with those? Well, we're going to find the eigenvectors with them. So a long boring story here. So when lambda is 5, we need to put that in the form of this thing and solve equal to 0. So the matrix M minus lambda I. So we're going to take 5 off all the diagonals basically. So first diagonal was 1. So 1 take 5 is minus 4. 6 take 5 is 1. 4 take 5 is minus 1. And then if you multiply all those out, you'll get and then you can mess about with them if you like doing simultaneous equations. I'll show you a shortcut in a minute. 1, 2, 3. You could mess about and say, well, if I do equation 1, take away 4 lots of equation 2, what would that do for me? Well, that would do gone, gone, 3z, and 0 take 4 noughts is 0. So that gives you z equals 0. And then you could put that in here, and you get 2x minus 2y equals 0, which leads you to the fact that x equals 0. So x and y equals 1. And then your eigenvector, well, we know is, it can be lots of multiples of this, but we know z is 0, so put that in there. And we know x is y, so you can pick any number you like, 1, 1. Easy, done. Do 2 if you prefer. Quicker way to do that would be to go to simultaneous equations on this calculator. So if you go exit menu, equation mode, pick simultaneous, pick unknowns 3, put those values in, 4 minus 4, 4 minus 1, naught. You have to put in the naught in as your d value. I'm sure it wants equals something. So put those in, minus 1, 1, minus 1, naught, 2 minus 2, and minus 1, naught. And if you put them in and press solve or exe, you'll get infinitely many solutions. It'll tell you that y equals x, z equals 0. It's been like probably tells you that y is y. But therefore it gives you those things. You can do it from the calculator. And that's how I do it. Right, let's do another one. So eigenvalue is 4, so you take 4 off the diagonals. So that was 1 take 4 is minus 3. 6 take 4 is 2. 4 take 4 is 0. Right, so rather than doing all that business, let's put them in and you're calculating simultaneous equations. Minus 3, 4, minus 1, naught. 1, 2, minus 1, naught. So you're just changing the diagonals if you've done this. 2, minus 2, and naught. Press go. It should say infinitely many solutions. It tells you that x equals z. It tells you that y equals z. It tells you that z equals z. So basically, if x equals z and y equals z, and they all equal z. So they're all the same blinking thing. Or if you do this by hand, you'd find that x equals y equals z. So if they're all the same thing, then an eigenvector, they all equal z. So let's make z 1, so it'll be 1, 1, 1. Bingo. All right, move it on. The next one, when lambda is 2, so the eigenvalue is 2. So off the diagonals, you want to take 2. 1 take 2 minus 1. 6 take 2, 4. 4 take 2, 2. So let's put those in the calculator. All we have to do is change those diagonals. Oh, error. What do you mean error? I don't do errors. Right, next one. Touch off. Oh, no. 4. Change that one to a 2. All should be the same. Go for it. So this tells us that x equals minus z from the calculator, infinitely many solutions, y equals 0 and z equals z. Remember, I'm in simultaneous equation mode to do with 3 unknowns. So eigenvector from that. Right, so y is 0, z is z, and x is minus z. So if we let x be 1, then that's got to be a minus 1, hasn't it? You could have a minus 1 and a 1 there. I don't really care, but I've gone with that. Right, so our decomposition form will be our eigenvectors, and our eigenvectors are, I've forgotten them because they're on the other slide and I can't flip that. 1, 1, 0, 1, 1, 1. Oh, just find 1 more minus 1 and put notes in here. Those are the eigenvalues. The inverse of that, oh my goodness, we'll have to do that in the machine. Menu 1, put that in as a matrix. And then shift 2 to the power. No, I've got to put the matrix in first, haven't I? Do we get? Yeah. Minus 1, 1, 1, 2, minus 1, minus 1, minus 1, 1, 0, super doop. And then we'll have to empty the 5, so you put those to the 5. Good grief. And stick these in. Oh dear. So to put that in as a matrix, and then you want to do like mat. Oh no, you don't even need to do that. So if you call that one A, you do mat A times mat. So you have to put that one in as your mat B. A inverse, and then out will come da 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 this matrix. Yeah, he's a big boy. I'm going to squash that one on. And there you have it. I can't put the end bracket on. Woof! Right, one for you now. See if you can have as much fun as me. Right, here's one for you. Keep you out of trouble for 10 minutes. Find the eigenvalues, the eigenvectors, put them in the decomposition thing, and then find m to the n. I'm going to change that because that's really boring if you have m to the n. You have to use your calculator a lot. Let's change that to m to the 6, just to speed things up. So I'm not fretting about it. Right, off you go. Please press pause and give this a whirl. I'll run out of tea. Let's press pause. Anybody remember that song about the kings and queens? William, William, Henry, Stephen, Henry, Richard, John. Henry, then come 3 Edwards. I can't remember it. Richard, Henry, whatever it was. But here's my cup. It's very interesting. I don't know if you can see it. I'm sure you can. There we are. It's got all the kings and queens on. I like that one. Anyway, so hopefully ready. You've had a go now. You've unpaused. Here come the answers. Eigenvalues are 4, 6, minus 2. The eigenvectors, I made a meal of this, I did it by hand, but you could remember to do it on your calculator in simultaneous equations. You get minus 1, 0, and 1, 0, 1, and 0, 1, 0, 1. Then when you put it in the decomposition form, you get that. So m to the 6 is that. Stick it in your machine, and out comes that. Well, well, well. That's the end. So now go and have a break, and then exercise 6F. How much fun is that going to be? Page 146. So this is the end. You'll be a little bit upset to hear of all the new material. Lesson 8, it is more of a just watch and listen. You'll find really, really interesting because it's a summary of the matrices that we've done. And it actually explains what the purpose of it and why we did it. So you're going to enjoy that one if you didn't enjoy this. But you've enjoyed them all. I'm sure you've loved it. Here we go. Have a go at 6F and then summary lesson next one, which is with someone slightly different to me. But it really, really, really is a worthwhile video to watch, as you'll see. Anyway, okay, bye for now. Don't get up to trouble, and I hope you stay well.